Started recording. Are there any questions? Well, questions from last time I'll take later. So today we will do something about zeros of polynomials. Okay. So here is something which you may find interesting. Okay. So let me show you this. Oh, what happened? Oh, that is somewhere else. Okay. So hold on. Sharing is a bit of a pain here. Okay. What happened? Okay, this became. Oh, why can't I enlarge it? This is a bit weird. I don't know why I'm not able to enlarge it. Maybe because this is here. Yeah, what?
You could try sharing the screen and then enlarging. I don't know that.
Maybe I will do that because maybe to start with, I'll do that. Maybe that is better. Maybe I just share the screen. But still, I'm not able to enlarge this for some reason. Very weird. I mean, because I'm on the same. Yeah, what the hell is this? Oh, okay, so now it comes. Yeah, but it's putting it on next to each other, which is the irritating thing.
Can you pull the bottom right of the Wolfram window?
No, I'm not able to do that. But okay, maybe I will just settle for this much. It's a bit. So yeah, no, there's something stupid is happening. I don't know what. Okay, so what I want to do is, so the question is this. Okay, just I want to show some pictures. So suppose you take a random polynomial. Okay, so what do I mean by random polynomial? You take a polynomial of degree n, where the coefficients are, let's say, IID random variables. You can put IID normal 0, 1 random variables. You can put IID plus or minus 1 random variables. You can put something else. So then the zeros, the roots of the polynomial, there will be n complex roots, right? So where are they going to be? They will also be random. So question is, what do you see? So if you have never seen this, you will find a surprise here. So here I have written the code already. So forget all that comes later. That's some junk from something else. It is only this part which I'm worried about. So here I have taken 80. N is 80. Yeah, you can take 50 also, is fine. So I have taken three things already. X is 2 times, this is plus or minus 1. Okay. So so X will be plus or minus 1 with equal probability. Y is normal random variables. Okay. So Y consists of a vector of normal random variables. Y1 consists of a collection of Cauchy random variables. You know, Cauchy is a ratio of two normals. And the thing is, Cauchy is usually ill-behaved, right? It's heavy-tailed. Okay, so I have taken this plus minus 1, normal, and Cauchy random variables. These are sequence of independent random variables, or at least pseudo random numbers. And then what I do is I take the polynomial with these coefficients. So x of I, t to the power I minus 1. Since these are indexed 1 to n, I have to shift so that the coefficients go from t to the 0 to t to the n minus 1. These are polynomials of degree n minus 1. So I just find all the roots of it. That's what z is. Z is all the numerically found roots of the polynomial with coefficients x. And w is similarly with coefficients y, and v is similarly with coefficients y1. Now, what I want to see are the roots, which is the code for here. So let's do it and see. So if I run it, you see the picture, right? So is this visible? This one. So you see that the roots in the first case, z, this is for the zeros of the polynomial with plus minus coefficients, are approximately on the unit circle and equally distributed, it looks like. For normal also, it looks exactly the same. Okay, and for Cauchy, it also looks exactly the same. In fact, it looks even better actually, but that's another matter. But this looks very uniform. So what is happening? So this there is a theorem obviously here. The picture shows a theorem, so you have to make it a theorem. So why is it that the zeros are on the unit circle, and you also see they are well, they are not exactly on the unit circle. That is not true. They are not exactly on the unit circle. However, they are very close to the unit circle, but in angle, they seem to be uniformly. There is no bias towards a particular angle or anything. That at least we don't see it in the pictures. So this is a fact, and what I'm going to do today will imply these things. Actually, we'll do something which is much stronger than all this. Okay, so that's what I want to show today. Is okay? I mean, any questions? I mean, so it's one of the surprises for people used to probability is that Cauchy behaves like normal and plus minus one. That is something that you will also see why. I won't do much of the probability part. I'll do something that's not probability, but still, yeah.
Manju, so if n becomes larger, this more on
Yeah.
the like yeah.
Yeah, so it is converging. So I have just shown it for 80. If you like, I can go for, okay, let's try 150. I mean, it will give something. I don't know whether, yeah, one should be a bit cautious when doing this. You see slightly better. So I went to 150. You see that they're sticking maybe a bit closer to the unit circle. In this case, there may be a bit more dispersion, but the it is true. So you can go. I mean, I don't know what it is giving. One should be cautious when doing this just invoking. You see that the zeros are approximately uniformly distributed. There are some stray zeros, but that seems to be small in proportion, so negligible. So most are on the close to the unit circle and uniformly distributed. Why is this? So how do we prove this? Okay. So this is what this will be done by what I am doing going to do today. Okay, so I'll close this. Are there any other questions? Does anyone want to see any other thing here? So, okay, so then let me just close this. Okay, so now let me share the OneNote. Oh, it's not showing the OneNote. Okay, so that is because it's on another desktop. Irritating fact. I know how to do it now. Okay, so let me just. Sorry about this. If they are on different desktops, then it doesn't actually show. That is the stupid thing I want to share. Again, it opened in a different desktop, I think. Okay, so okay, maybe is screen share, was it okay? I mean, so can you see if I screen share, do you see the notes or is it not so well?
It's normal.
It's okay? Okay, so then I will stick to this, okay? So what we want to do is show theorems like this about zeros. But before that, are there any questions about the Erdős-Turan equidistribution like theorem? This one, we showed that if you have any probability measure on the circle and uniform measure on the circle, then for all arcs, the difference in the two measures can be bounded in terms of the first few Fourier coefficients and 1 over n. So if you get good control on the first few Fourier coefficients, you get a bound of roughly order 1 by n. If this is all 0, for example, then you get 1 by n. So that's the idea. Any questions or comments so far? I mean, on that? If not, let me give application of this, which is zeros of polynomials. Okay, so there won't be anything random. Random part I will leave to you as exercise. It's much more powerful than that. Okay, so what is it that, so P is a polynomial. Okay, so P is some polynomial we'll take with complex. plus a naught, where ai's are of course complex numbers. And then let's say the roots are, we can also write this in terms of the roots, which is z minus maybe zeta 1 dot 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 z minus zeta n. Okay. So there are two things. So we want to say, so for many polynomials, so the motivation is for many polynomials. Of course, roots can be anything for a degree n polynomial. For many means maybe typical polynomials. Two things, roots are approximately, okay, I'll break it into two things after writing what I had shown in pictures, approximately uniformly distributed on the unit circle. The unit circle, okay. So this really involves two things. So what we should do is two things. So one is radial distribution. We split it into two parts. So this really has two parts. One is radial distribution. So get an upper bound for what? What proportions of, let's take delta at mod zeta j. Okay. Okay, so this is the radial distribution, but what do I mean to say? The radii should be close to 1, right? The radii should be close to 1. So that means, let's say we take something like indicator mod zeta j minus 1 bigger than epsilon. Okay, and show that somehow this is small. Second part is angular equidistribution. So similarly, get a good bound for. Now what we look at, not the we don't care about where it is, so we don't care about the radii, we only care about the angles, which means we'll take zeta j over mod zeta j, right? So that will give me the zeta j over mod zeta j will give me a point on the unit circle. So let's take that belongs to an arc. So we'll take j equals 1 up to n. This is to be compared with, here all the radii are close to 1. So anything away from 1, we want to bound it. Here, what we are not going to say this is small. This is supposed to be what? What is this supposed to be? It should be close to m of I, right? M of I, remember, is the arc length over 2 pi. Okay, so we want to get a bound for this. Something small. It's not always small, because it's not true that all polynomials have this property, right? I mean, you can take a polynomial where all the roots are on the real line. So it's not true always that it is small. But we will write bounds and then see when it is small. Okay, and then that will give conclusions. So this is for any arc. So maybe even sup over I contained in T an arc. So over all arcs, we want to bound this kind of stuff and this. So these are the two issues. Actually, this is somewhat easy, and we'll do it later. Okay, so this is the key thing. This is the non-trivial, very non-trivial part. And that is what I want to tell first, because I'll come to that later, or maybe I will even postpone it to exercises. Actually, I wanted to tell one thing. The thing is, Friday I will not be able to take give the lecture. I'm going somewhere else to give a lecture, and it's so far away I cannot manage both. So I will just cancel Friday's class. Okay, I mean, if needed, I can always put up a recording, but I think it's okay. We have had enough classes, so it's okay to miss one, I guess. So I'll cancel Fridays. So I want to wrap this up today. So if I don't get to radial distribution, I'll put it in notes and you can read it up and so on. This is the key thing that I want to emphasize, which is the Erdős-Turan It's a theorem of Erdős and Turan, which is in context of which they developed that other technique. Okay, what they say is that, so take any polynomial like this. So the bound is, so let's give this some names. Okay, let P be as above. So let me introduce some notations. So and zeta j, let's write as rj e to the I theta j. Okay, be the roots. Okay, and we will make some assumptions also. Assume that a0 and an are not 0. Okay, I will assume that is actually of degree n, and also the constant coefficient is not 0. It's not a serious issue, but let's assume that. Okay, so the way the bound is written will use that. So this is a small assumption that it's not 0. Then also let me define another thing. Let mu p be the angular measure. So okay, so delta e to the I theta j. So this is a measure, a probability measure on the unit circle. This is the angular distribution of roots. In other words, so mu of a, if you write mu of a, so mu is a measure on the circle. If you take mu of an arc here, then what is it measuring? It is measuring the proportion of zeros which lie in this sector. If this is I, mu of I is the proportion of roots of P in the sector. Because we project everything to the, I mean, we just remove the radial part. So we radially project it to the unit circle. So this is what it is measuring. So the conclusion is then mu of I minus m of I, you can take sup over all arcs. For all arcs, this is true. Sup over I arc is bounded by what is the quantity that bounds. So there is some constant which is not too bad. I can put 10 or something like that. It's much smaller than that. So C over square root of n times h of p. Okay, n is the degree that comes here, and h of p. What is this h of p? This h of p is in some way measuring the size of p on the unit circle. Okay, so it is defined as integral 0 to 2 pi log plus mod p of e to the I theta over square root of a0 into an absolute value. It is this log plus. Okay, log plus is the positive part of logarithm. Okay, so and d theta over 2 pi. Okay, so this is a measure. So this measures size of p on the unit circle. Okay, so here log plus x is, I mean, we are applying it to absolute value. Log plus of a positive number is log x if x is bigger than or equal to 1, and 0 if. Okay. So that's what, it's the positive part of logarithm. So this is a measure the size of p. Okay, so you may find, so in some sense, this is small. To say this is small, you have to say that this is small, that this quantity is not too big. Sometimes it is big. It can be big because it should, something should go wrong, right? I mean, because all polynomials are not going to have this. So maybe we can see some example, but before that, it's a bit hard to, so easier to understand. Is there a question?
Manju, I think you need the square root of h of p, right?
Yeah. Sorry, I forgot. Thanks. So this is not h of p, but square root of h of p. Thanks, Kaushik. So it is square root of h of p, and this is also square root of n. So easier to understand. I mean, easier bounds. Easier means easier to understand. Here you are taking log plus and then taking this and so on. So, but it is easy to bound it by things you can understand better. So, for example, h of p is bounded by, you just put the, see, log plus is bounded by, of course, integral 0 to 2 pi. Log plus is bounded by the absolute value of the log, right? Okay, this is not particularly better either. I mean, this is still integral of logarithm. Okay, you can write it like this. Just that this is better than this. But this can be bounded. A simple bound would be just to take the sup norm over this. This is an average over the circle. You can just bound it by log of p over square root of a naught into a. Okay, where norm p is the sup norm on t. So that is one way. But even easier, I mean, even worse is how do you bound p? I mean, p of z is this. How do you bound mod p of z? You put the absolute values on all the terms. If z is on the unit circle, those things will go away. They are 1, right? Z to the n, z to the n minus 1, absolute values are 1. So an even simpler bound just in terms of coefficients is log of absolute a naught plus dot 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 plus absolute a n divided by square root of a naught times a n. This is the way to bound this quantity, that h of p. So maybe these are easier to understand. For example, let's go back to the random case. This is the only time I will do the random case. So example, suppose ak IID plus or minus 1. Okay. So then h of p is bounded by what? All these are 1. Absolute values are all 1. So you just get log of n plus 1. Right, because there are n of them, n plus 1 coefficients, so log of n plus 1, so which gives that this mu of I minus m of I is bounded by a constant log n over square root n. Okay, log n plus 1, nobody cares for the difference, but I have here square root. Okay, I forgot the square root again. So square root log n over square root n. So it's very good bound. So it is very small. So for all I arcs. So you see that in the, this already proves that in the plus minus case, you have that the angular distribution is very close to uniform. For large degree, it is very close to uniform. So this is small. As n goes to infinity, it goes to 0. So you get a, not only you get even a bound at the rate at which it is almost like 1 by root n. It's okay, slightly worse because of the square root log n. Is that okay? What if AKs are plus? What if AK are IID Cauchy? Cauchy random variables tend to be big, but how big? It still doesn't matter. So you can say that probability mod AK bigger than, let's say I want to say it is bigger than, I want a bound for mod AK. How big can it be? Okay. Okay, so if I put a B here, what's the probability that it will be either smaller than B or smaller than 1 by B or bigger than B? Okay, you can see that if you understand the Cauchy distribution, you will get that this is some, I don't know, something like 10 over B. Okay, so that's See, probability that AK is smaller than 1 by B, the Cauchy distribution has density 1 over pi into 1 plus x square. So what's the probability that it is going to be between minus B and plus B, minus 1 by B and plus 1 by B? It is the supremum of the density times the length of the interval, which is 2 over B times the density is maximum 1 by pi. So you'll get 2 over pi B. And then Cauchy also has a property that 1 by A and A have the same distribution. So probability mod A bigger than B is same as probability mod A less than 1 by B. So you get something like this. Okay, so you get some bound. What this means is that, thus, if Bn is, so this implies that probability that 1 by Bn less than AK less than Bn for some K. For some K between 0 and n, that probability is bounded by 10 times n over n plus 1 over Bn. Okay, so let's take Bn to be some n to the 5. I mean, n cube will be okay. So that with probability greater than equal to 1 minus 1 over n to the 4, or 1 minus some constant over n to the 4, all AKs are between, what is it, n to the 5 and n to the minus 5. So this is a very good probability. I mean, if you know Borel, Cantelli and so on, this is something that is summable 1 over n to the 4. So what it means is, so forget this. So with very high probability, all the coefficients are between n to the 5 and n to the minus 5. So what bound then under this event, when this happens, the bound for h of p is going to be, we will just use this.
So Manju, there is something, the way that you have written it, I mean, wait 1 second, with probability bigger than 1 minus, but that statement is different what you have written, right? So there's something fishy.
No,
It's a complement of that probability. In the first line, you have to write.
Yeah, so that's the.
Oh, sorry. This, okay. Sorry, this is not okay. So this is actually, sorry. I mean, this is actually at least. This is at least 1 minus probability. It does not happen. So AK has to be less than 1 by B or bigger than B. That is like this. Therefore, this is at least 1 minus 10 times that is greater than equal to 1 minus this one, where you get a union bound for the bad events, which gives you this extra n plus 1. So if I take n to the 5, then I get 1 minus constant over n to the 4. Probability with which all these are n to the minus 5. Actually, you will see that it doesn't matter what power of n I have here, because my bound for h of p has a log here. So will be, in this case, what will be the sum of absolute values? So will be, so mod a naught an will be also at least, so it will be less than equal to log of a naught plus up to an. Let's say log plus of this plus log plus of mod a naught an square root, right? Anyway, all these are small. I mean, they are all powers of n. So this whole thing is bounded by some constant log n. Because this is n times n to the, this is n into n to the 5 maybe. So what will be the log? It will be 6 times log n. And this is also log n. So overall, h is still bounded by log n actually. Okay, it doesn't matter that the coefficients are that small. So
the only problematic case is when one coefficient is exponential in n.
Right, that is exactly the point. So just let me conclude. Yeah, it's what Somendu said. That is where things can go wrong. So we still get mu of I minus m of I bounded by some constant square root log n by n, square root n. So still small. So what does it take to really violate this? Okay, so when is this problem? So the log should be a problem. The log should create problems for this square root n. That means this quantity should be exponentially large. at least like e to the square root of n and such things, right? Or no, e to the n, because we have square root on both sides, so it should be constant n. So problematic case is when this kind of thing, the b turns out to be something exponentially large, and for that you will see that so unlike the usual things in probability, as long as expectation log mod ak, let's say with this is finite, then we get equidistribution of angles. Okay, so this is amazing. So it's not like the usual one where first moment, second moment are the matter, but it is this. Okay. Any questions here? So how you get these conclusions? I mean, this I have written. If you may be able to see it or you may not, don't worry. But if you understand these cases, at least it's okay. So this is a very, very powerful theorem, and it's better because there is no randomness. Okay, see, randomness is not good. For example, look at something like Weyl equidistribution. So we, as probabilists, we are used to saying things which are, almost surely and so on. But think of something like this. Weyl's theorem says that I mentioned that Weyl's theorem, the first one, is a special case of, Birkhoff's ergodic theorem. But Birkhoff's ergodic theorem says that what Birkhoff's ergodic theorem says is that for almost every alpha in the real line, this sequence n alpha is equidistributed. But Weyl's theorem says that for any alpha which is irrational, this is equidistributed. Which is better? This is better because it actually identifies what is the problem. So when we say almost surely for almost every alpha something happens, it's a bit of a cop-out because we admit that we don't know what it is that makes this happen. So, but I know that for most alphas something will happen. But if you can actually quantify what is the property of alpha that will make something happen, that is better. So that is called de-randomization. In computer science, they always try to do that. It's a better theorem. So that way, Erdas-Turan is already a de-randomized theorem. There is nothing. It already tells you that this happens provided you can control P on the unit circle. Okay. So, okay. So that's what. So now I want to give the proof of this, which now it looks like I will not be able to end it. But anyway, I will start.
Manju, is that tight? Like is there a polynomial for which this rate is faster, like smaller than 1/17?
Yeah. So what are some violations? That is also a good question. So to violate, so let's take something like z minus 1 to the n. So all roots are equal to 1. So hardly equidistributed, right? I mean, everything is on the positive line. So far from equidistribution. So what can we say about this one? Here you see at least that, well, okay, I don't want to get into this log integral. Maybe I can do that also. It's not such a problem. So then, so A0 and A1 are both 1. A0, AN are both 1 here. Okay, this is monic and last coefficient will be, well, at least absolute value is 1. So h of p in this case is actually 0 to 2 pi log of absolute value z minus 1, and then I get an n because that log plus, but okay, log plus in this case. So here you have the unit circle, and I have taken, okay, so I have taken 1. So okay, so let's say log plus this. Log plus, we get e to the I theta minus 1 d theta over 2 pi. What it means is that log plus means points which are at distance more than 1 should only be considered. So from this you draw a circle of radius 1. So, okay, I mean, they don't look to be the same size, but they are supposed to be. So here the log plus is 0 because the distance to 1 is 0. So it is only this part that contributes. But still, whatever it is, you see that it is something proportional to n. So the constant is whatever is the log of mod e to the I theta minus 1 on this arc, which is something. Okay, I don't need to figure it out. It is bounded below by a constant n. So you see that this is problematic, that h of p over n is big in this case. Is greater than or equal to a constant. So this is not giving equidistribution. So this is, in that sense, it is okay. This is not. This is an example where it shows that this is the way it happens.
I guess the middle coefficient is like n choose 2, which is exponential in n. That
right.
You can also
yeah.
use.
So what's happening? Yeah, even that, I mean, easier than h of p. Yeah, that might have been better. If you look at this expression, of course, this and that could be different in principle, but if you look at this expression, some of the coefficients are extremely large, like binomial coefficients, which are exponentially large, right? So that's why it's not going to work in this case. Coefficients have to be somewhat controlled, not exponentially large in n. That's the main point. Okay. So incidentally, for those who are interested in probability, this condition is not relevant. I mean, this was also shown without any assumptions for any IID non-degenerate random variables, you get equidistribution, but that uses randomness to a certain extent. This is without using randomness actually. Okay, let me come to the proof of this. So I will, it will spill over to the next one. Then I will probably also do the radial part. Okay, so now let's do the. So first case is always the way it is done. So case 1, assume roots are on the unit circle. So our P of Z is actually an times product Z minus zeta J, where zeta J is actually on the unit circle. So there is no R, it is e to the I theta J. Okay. So let's write like that. What have I done? Yeah, okay. So there's no RJ. RJs are all 1. That's what we are assuming. Okay, so we will come to that. Why? I mean, so but this is the key point to do this for this. Now, so mu is just so then our angular equidistribution, there is no radial scaling required because they are already on the unit circle. So this is the measure which puts mass 1 over n at all the e to the I theta j's. So by the Erdős-Thüren lemma, we know I mean the equidistribution lemma, we know that the supremum over all arcs, mu of I minus m of I, can be bounded by a constant times sum of k equals 0 to k equals 1 up to n mu hat of, okay, let me not use this n. This n is now the degree. So let me use a different, so let me use a capital N for mu hat of k over k plus 1 over n for any n. So we have to choose an appropriate capital N. We will come to that. This is true for any n by the Erdős-Thüren lemma. So the question is how to control. So how to control the Fourier coefficients? That's the main thing. If I manage to control the Fourier coefficients, I get something. What is mu hat of k? Mu is this. So mu hat of k is just 1 by n e to the minus I k theta j, right? Right, mu hat of k is just this, right? E to the minus I k theta j, because this is an atomic measure. So how do I control this kind of stuff? E to the I theta j's are the, so this is actually, so but the reason we can control this is, I mean, something like this we saw in some context. Now I forget. So this is, so no, so just as a side to, we will get a bound for this. But the point is, this is same as 1 by n summation zeta j raised to the power k. It is the sum of kth powers of the roots. So when k is 1, this is an minus 1 by an, right? And when k is 2, you can write. So this can be, this is actually a symmetric polynomial of the roots. It's a symmetric polynomial of the roots. Which implies that it is actually a symmetric polynomial of the coefficients. Okay, so these are called Newton's identities.
Yeah, so we saw this in that Piso Vijayaraghavan.
Okay. Yes. Right. So when we are doing the sum of powers, right, that's how we showed theta to the n is close to this, an integer. So this Newton identities tell you that this is, but that will not be the best way to do it now. We'll do it in a different way. Okay, we'll do it a bit differently. But this is the intuition that this kind of quantities can be expressed in terms of the coefficients, and ultimately that's what I want. At least if you don't bother about h of p, but you want to get it in this form, somehow you have to get the coefficients. So that is where that will come. But we will bound it in a different way. Okay, so we'll bound in a different way. So our claim is that this is actually, okay, so let me just look up the expression in my notes, then I can right. So the claim is that it is, okay, 2 mod k over n, okay. So the claim is like this. We'll find a different expression that mu hat of k is 2 times mod k. Actually, for me, k is positive, but anyway, so for any k, this is true, 2 times mod k times the integral 0 to 2 pi log mod p of e to the I theta over square root of an, sorry, not square root, just an, times e to the minus I k theta d theta over 2 pi. Okay, so this is the expression for mu hat in terms of our polynomial. And you see the terms coming out here almost, right? The log integral is already showing up. A naught is missing, but that's a simple point that once you do this, a small consequence of this is that you see that A naught is actually an times the product of zeta j or minus zeta j times minus 1 to the n. Right, if you see the constant coefficient is an times the product of these roots times minus 1 to the n, which implies that a naught and an have the same absolute value. If all the roots are in the unit circle, this has to happen that a naught n. So what I have as mod an, you can also write as square root of a naught into an if you want. So that's why that is not showing up. So don't worry about that, but this is more or less getting it in the form that we want. But okay, let's maybe complete it, assuming the claim. Assuming the claim, what we get is that mu hat of k over k absolute value is bounded by, oh sorry, there is an n I forgot. So because mu hat also has the factor of n here, so there will be a 2 by n here. Okay, so what I will be left with is 2 by n times, so I put the absolute value. Now, why do I get log plus? So let me do one thing. Let me not try to, this will be a slight distraction to get this in the h of p form. So let me get this intermediate form. Okay, it's a bit easier. Just then we can go back and see why we get the stronger form, which is h of p. I will try to get it in this form. So which is almost straightforward here, because what I get is, so from this, if I do mu hat k by k, absolute value is bounded by 2 over n. And here I just bound it by the maximum, right? So I can bound it by log of the maximum of the log is log of the maximum. So norm of p on the unit circle, this has absolute value 1 divided by an, which is same as 2 over n log of absolute value norm of p divided by square root a naught an, because a naught and an have the, that is for the last step. So we got everything actually. So we got this. Hence, if you look at this quantity, sup over all arcs, mu of I minus m of I will be bounded by what? This 2 times n, so will get me constant, a different constant over n. What I get is k equals 1 to, now this is something completely different. Okay. So I get k equals 1 to capital N, and for each of the bounds, it is I get norm p over, oh sorry, there is a log here, log of norm p over a naught an absolute value. Well, let me write it properly. Sorry. So all the bounds are actually the same. For mu hat k by k, the bounds are the same. So let me just write it as c by, this is small n. Here I am applying with some capital N, which is yet to be chosen. So I get capital N times log of norm p over square root a naught an plus 1 by n. Okay, what is the best choice of n? So it's up to you to choose n. So this is true for all n. So you have something like n times a plus 1 by n. What should you choose to minimize n? Always you can do the optimization if you want. The best is to arrange it so that both terms contribute equally. See, when n goes bigger, this is better, but this is worse. So if you optimize it, you will find that the best is when both contribute equally. So best choice is, but I don't need to justify for you it is best choice. This is my choice. Is when na equal to 1 by n, which is n is 1 by square root of a. So let's choose like that. Okay, here my a is this quantity log of p over square root a naught an. So I will leave the optimization to you, but I choose n like this, 1 by square root of log norm p over square root a naught an, or nearest integer to that. Okay, what I mean is you have to choose it an integer, but you choose it one bigger or something like that. It will not matter. There is constant, you can absorb bounded by 2 factor of 2 and absorb it there to get. Then this becomes capital constant over n. You see that 1 over n, both sides are equal. So 1 over n is 1 by square root, sorry, something is fishy. 1 by n, right? So, okay, 1 by n will give me the square root of this. Which is the bound that I wanted. I mean, if you take this one, log norm of p divided by square root a naught an. Okay, is that okay? This is the intermediate bound. It's the intermediate bound. Now, if you want to improve it, okay, maybe let me finish rather than doing this. So how do you improve it? Okay, or maybe I just say how to improve to sorry, this something is still fishy, right? Why did I get 1 by n? That should have been square root also. Ah, okay. Sorry, nobody caught my mistake. What's the mistake? See, this is c over n. Here I should have gotten square root n, right? I mean, 1 by square root n square root of this. So 1 by square root n times square root of this is what I should have got. Why did I get 1 by n? See, the bound for mu hat k by k, this is going into the, this is not outside, it is inside. So this c over n is, there is no c over n. C times mu hat k by k is bounded by this. So I absorb the 2 outside, that I don't care, but what I have here is capital N over small n. Small n is the degree. Okay, so this is yeah, so this is 1 by small n times this. So I have to choose capital N to be in the square root. There is also a small n. It is whatever n is 1 by square root of a will have also this one 1 by square root. So when I do 1 by that, so I do get a square root here. Okay, is that okay? I mean, did I go fast and lose people or something? I mean, is it okay? Okay, so I'll assume it is okay. So we got the intermediate bound. So can we get the, how to improve it to the other bound? Maybe I will, how to improve to c over square root n. So the idea is, don't bound it like this. So we had a bound mu hat of k by k, we had this, right? So from the claim, what you do is from the claim, right? So instead of putting the sup norm, you just write the integral. Okay, so we get mu hat of k by k, you bound it as 2 over n times integral 0 to 2 pi. This you have, right? So you have the logarithm. Okay, so I'm going to put the absolute value. So we'll write, well, we have to put the absolute value. But what I want to do is, yeah, how do I don't want to put the absolute value in. I put the absolute value inside. That's okay. Right, absolute value is okay. Log of mod p of e to the I theta over so I just put the absolute value inside the integral. This one is absolute value 1, so I get this. But the absolute value of any number, see, if any number you write as positive part minus negative part, then the absolute value is positive part plus the negative part, which is same as positive part minus, is it, so how do I write? If I do, yeah, if I add these two, yeah, is that right? Sorry, mod x plus x, mod x plus norm, sorry, no, what am I writing? What is it in terms of x plus and x? X plus x mod x is 2x plus, so it is actually 2x plus minus x, right? So you can write it like that. So this integral can be written as 2, because I want log plus, I can write it as log plus mod p of e to the I theta over square root a naught a n d theta over 2 pi minus, okay, 2 times, so this becomes 4 by n minus 2 by n without any absolute value. There is no absolute value here. And this is actually, I think this is 0 or something like that. Or maybe you get log it. So this is 0. Okay, I won't explain now. So this is h of p. So that's how you get h of p over n instead of the subnorm of p over n. I mean, that's what instead of this. So this is the h of p. Okay, so that's how you would improve it. Hey, any questions here? But don't worry. I mean, this is just as good. In most applications, we just use this. If you don't want, this is a sharper form. Okay, some references. So maybe I have taken this from two things. So I actually learned this all from Sodin first, Mikhail Sodin. He had sent me some notes, some unpublished notes. On all this, on this as well as the previous equidistribution theorem I proved. So I learned it from there, but there is also a nice short paper by Kannan Soundararajan. So it's on the archive, you can find it. If you just go to Kannan, he's a very famous number theorist. So one of his papers is about Eudastugan, you will find it. So that has it in the stronger form of h of p. Okay. But in actual most cases we apply, we just bound it by this simpler one. So this is just as good. If you want, take that as the theorem. Okay. So two things remain: how to prove the claim and how to go from how to go for the general case. Okay. So I have only 1 minute. Maybe I will just take an extra minute and finish off how to do the general case. So remains, I need to prove the claim still. What if roots don't lie on the unit circle? Okay. What if roots are not on the unit circle? That is the very interesting trick by Schur. So this is called Schur's trick. So we have our polynomial p of z is an times z minus zeta 1 up to
it's 1 o'clock.
Z minus zeta n. I'll take maybe 2 minutes or so to finish this. Okay. So where let's write zeta j as rj times psi j. Psi j is this e to the I theta j. Okay. So then you make a new polynomial whose roots are just those. Well, there's no need for this symbol. Let's just call it rj e to the I theta j. So let's compare it with a polynomial whose roots are those. I theta 1. Z minus e to the I theta. Okay, so this is of the kind, this has roots on the unit circle. Okay, so if you look at the mu sub p and mu sub q are the same. What is mu sub p? I mean the angular distribution of roots, right? Where did I define that? I defined the mu sub p is this 1 over n summation, but you put the masses at the radial projections, right? I mean on the unit circle, but p and q have the same radial projections. Zeta j's will project to this e to the, so mu p is mu q. So so the mounts mu p of I and mu q of I are the same. So what are you trying to show? So you are trying to show mu p of I minus m of I is bounded by some quantity. Okay, so we already know this for q. So what I'm saying is it suffices to show because of this suffices to show that h of q over h of q less than equal to h of p. Because we know mu p of I minus the Lebesgue measure is mu q of I minus Lebesgue measure, which is bounded by square root h of q by n, and that is bounded by square root h of p by n. So it suffices to show this. When you go from q to p, this is what you want to show. But okay, Yeah. So what is h of q? Yeah. So which is also, it's enough to show, which is also implied. If I show that mod q is less than equal to mod p on the unit circle. Because what is h of p? I mean, it is the integral of log plus mod p and so on, right? It's the, or rather, okay, so there is a slight difference. Mod q over an. I want to show that is bounded by on the circle, because this is just the integral of log plus of this and log plus of this, right? So this is enough to show this. But more or less we have it here. So what is it? So this is actually, this is implied if what is q? Mod q of, let's say, e to the I alpha less than equal to mod p of e to the I alpha divided by square root of a0 by an. Okay, I just transfer it to that side for all alpha. This is what you want to show. But now you just write everything in terms of zeros. What is q? Q is an times product absolute value e to the I alpha minus e to the I theta j. J equals 1 to n, and there is also absolute value here. So question is this bounded by what is mod p? It is absolute value of an times product of e to the I alpha minus, now the roots are rj e to the I theta j. So you just write down what you want. Okay. J equals 1 to n, and divided by a naught by an is the product of the roots of p, right? So that will be square root of product rj, because a naught by an is product zeta j. Okay. So this is what you want to show. Anyway, an cancels. So what is it that implies this? You show term by term, this is 2. E to the I alpha minus e to the I theta bounded by square root r times e to the I alpha minus r e to the I theta for all r positive and e to the I alpha e to the I theta on the unit circle. This is an elementary inequality which I will leave as exercise. Okay. Sorry, my 2 minutes stretched to 5 minutes, but I'll stop here. That's a simple exercise, so I will stop here. So we will resume on Monday, where I have to prove the claim still, and then we will go for the radial distribution.